So question 1, how many letters are in my last name is not a statistical question. Okay, so no, it is not a statistical question. Make sure you answer that question. Okay, there's a question and then there's an explain. So you need to make sure you answer the question. Okay, and the explain is because your last name will always have one set of numbers. Yes. No, the reason it's numbers is because the question is how many letters are in your name. So how many letters are in your last name? 7. So the number is, you will always have 7 in your last name. Does that make sense? Okay, how do we change that to be a statistical question? Bella?
How many letters are in the last names of my classmates?
Yeah, how many letters are in the last names of my classmates? Because you're going to collect data, right? You're going to ask lots and lots of people. And all of you have different last names, so you will have a variety of data. Okay, 20.
Does it have to be answered like that?
You have to answer that it's not a statistical question, and you have to explain why or why not.
Okay.
So, okay. All right, B. What are the colors of the shoes worn by the students in my class? You guys said yes. It is a statistical question. Okay. And it's statistical because these shoe colors will vary. So you cannot just say yes or no. You have to explain the why. All right, so number 2 says the following members of the Arizona Supreme Court justices each served a different length on the bench. The following table lists how long, the number of years, each judge has served on the court. This right here is important because we need to know the length of how long, because when we write our sentence, because you know Eureka loves sentences, we can't just say 16. Right? You gotta tell me 16 what, okay? So 2A says calculate the mean, and it says show your work, okay? How many of you want a 4 on 2A on your test? How many of you want a 3 on 2A on your test? Oh, good. You all want a 4? You have to show your work. A 3 is you get the answer correct, but no work is shown. Got it? Okay, so what you should have done is taken the lengths of service and added them. So 9 plus 33 plus 24 plus 2 plus 18 plus 12. Okay, once you add all those together, you would have gotten 98. We're finding mean. Mean is an average, so we take our sum, 98, we divide it by 6, which is how many data values we have. Okay, and when you get 98 divided by 6, you get 16 3/10 with a repeater line. Okay, but remember I told you guys we were adding to the direction. And the direction says round to the whole number. So we're going to look at our tenths. Does the 3 make the 6 go up or stay the same? Stay the same. Remember, it's only a 5. 5 and up, round up. Okay? So really, this is going to be 16 And we're going to write a very lovely sentence that says the mean length of service in years is about, because we rounded, correct? 16 years. Okay? So, really all I did for my sentence was I took the mean length of service, okay, is about 16 years. All right? Reese. But remember I told you guys we were adding that direction in? You do not do it on the test unless it tells you to round. If it doesn't tell you to round, don't round. If it tells you to round to the hundreds, round to the hundreds. You round to what it tells you to. But we added that direction in. Okay, so 2B says calculate the mean absolute deviation. Who knows what mean absolute deviation stands for, Reese? Okay, but what's it stand for? What's that mean though? Like when we're looking for mean absolute deviation, what are we looking?
Average distance from
Perfect. Remember, mean is always an average, right? So it's the average distance away from the mean. Okay. So when we're looking at mean absolute deviation or MAD, we are finding that average distance away from the mean. So what's the very first thing we have to do when we are finding MAD? Bella?
add up all the deviations.
Ooh, is that the first thing we do?
Find the deviations.
Ooh, is that the first thing we do?
Find the mean?
Find the mean. Because you cannot do the MAD without the mean, can you?
No.
Find the mean. What Bella was doing, she's like, we already did that in A, right? Okay, so we already found the mean. Then what do, Bella? We need to find the deviations, okay? So I'm going to write deviations. Okay, so our mean is 16. So 9 is how far away from 16? Everybody? 7. 33 is how far away from 16? 17. 24 is how far away from 16?
8.
2 is how far away from 16?
14.
18 is how far away from 16?
2.
And 12 is how far away?
4.
4. So those are our deviations. It's the distance from the mean. Okay? So then we have those distances. So then what's the next step? We cadence? Add them all. So we're going to add 7 plus 17 plus 8 plus 14 plus 2 plus 4. When you guys added those, you should have gotten 52. And then it's an average. Okay, so we take that, divide it by the number of data points we have, which is 16. And 52 divided by 16 is 8 6/10. Repeater line over the 6. Do you need the repeater line? Yes. If 8's a continuation of a decimal, you have to have that. Could you have 8 66/100ths and the repeater line over the 66/100ths? Yes. Could you have 8 66/100ths and the repeater line only over the hundreds? The 6 and the hundreds? You can. There's lots of ways to write that. Okay, but make sure you have that repeater line. So the MAD of the lengths of service is 8 6/10 with the repeater line years. All right, so when we're looking at it, okay, we want to look at what our mean is. Our mean is 16. If we look at our lengths of service, we've only got 2 lengths of service that are even close to 16. Okay, so the rest are not. So 16 is not a good use to be able to say, yeah, most judges work 16 years. Because do most of the judges work 16 years?
No.
No, some have worked really long, some have worked a little bit, some are close to retiring and probably shouldn't be on the bench anymore. Okay, so you have to look at that. What else could indicate that it's not a good choice? What else lets us know, like, automatically that's probably not the best one?
It has a lot of variability
Okay, but how do we know that?
because
So how do we know it has a lot of variability? 20?
So like the deviations, 'cause, like, one
Not the
is-
deviations. Almost, but not quite.
it has a large spread.
But it has a large spread, but how do we know that?
Because it has a large mat.
It has a large MAD. Remember, you guys, this MAD is that definitive number that lets us know how large the spread is. We don't just say it has a large spread. We can use that MAD to give us a definitive number letting us know. But the main thing for this one is the fact that there's no other answers by the 16 at all. Okay? So, flip on over. Okay? So, the mean is not a good choice. Because there is not a lot of data by 16. Remember, use that evidence. Like, let me know what the mean is. Okay? So when we looked at it, we had a cluster that was higher, and we had a cluster that was lower than our mean. Okay? Right, the following table displays data on calories for several Campbell's soup choices. A says round the calorie values to the nearest 100 calories and use these rounded values to produce a dot plot of the distributions of the calories in these dishes. So what's step 1? Olivia? Yeah, you need to round the calories to the nearest 100 calories. Okay? Then your second task is to produce a dot plot. Okay? You're going to want to make sure you do both steps. Okay? So, if smoky ham and potato with cheese, okay, has 210 calories, what are we going to round that to? Tyler? 200. We're rounding to the nearest 100 calories. What would we round 360 calories for our Mexican style chicken tortilla? What do we round that to, Reese? 400? Yep. Okay? So go ahead and continue doing the rest. So first of all, for your rounding, you should have 400 for chicken noodle, 200 for creamy chicken, 200 for clam chowder, 400 for broccoli cheese soup, 200 for fiesta chicken, and 300 for vegetable melody. Okay? So on your dot plot, do you have a title?
Yes.
Okay, has to say dot plot of whatever you're measuring, whatever you're talking about. Okay? A reasonable scale for this would have been counting by 100s, correct? Would counting by ones have been a reasonable scale? Would counting by 50s be a reasonable scale?
No.
Okay? Yes, this wouldn't be too bad, but when we're rounding to the hundreds, okay, hundreds is the reasonable scale. Okay, and then did you label at the bottom what the numbers represent and said calories? Okay? If you don't have on your dot plot all of the pieces, which means you don't have the labels, you don't have an appropriate scale, and you don't have the dots in the right area, okay, you're not going to get a 4. So you gotta have all of the pieces. Now, obviously, some of you guys have different titles, okay, but all of you should have calories down here because that's what the numbers represent. Okay, Joanie.
So, I made mine really small. Is that
Okay.
like keeping phones taken off?
I just need to be able to clearly read it.
Okay.
Okay, Jenna.
Wouldn't you have to put in cups or something?
Okay, so Jenna's question is, do we have to put in cups? Look at your measurement. There's all sorts of different things. And these are just measuring calories. We're not saying calories in a cup of soup because this is 3 cups of soup. It's 400 calories. So on that one, you can just say calories. Okay, is that?
What if I put Campbell's soup choices in calories at the bottom?
Wait, say that again?
Campbell's soup choices in calories and I put in calories in parentheses.
But this bottom one measures what these numbers are, and these numbers are calories.
So I just
So
would put calories.
you would just put calories. Okay? All right. B. Okay, it says describe the distribution of the calories in these dishes. So go ahead and do that on your whiteboard. Go. Okay, so all of the discussions that we just had, everyone that discussed got a 2 because you only talked about one thing. Okay, when we are describing this distribution, we need to describe it as a whole. So we cannot just talk about one individual item. Okay, you need to talk to me about the shape, which Zach said the shape. But that's it, right? Okay, you have to talk to me about variability. Okay, which was all the people that were like, oh, it goes from here to here, or it has a small spread. Okay? That's variability. And then you need to talk about center, which is what a lot of the other people did. The other third said, most of the data is around this and that. Okay? You have to talk about all 3. Does that make sense? So when we're discussing this, we want to discuss all 3. So if we look at this, if we want to do our shape, okay, what would you guys say the shape of that diagram is? Kaylin? Bella?
Skewed right?
It's skewed right because we've got this, here's kind of like the top of our mound, okay, and then we've got this longer tail way over here, okay. This longer tail is on the right, so it would be skewed right. I would give it to you if you said slightly skewed right. It's not symmetrical though, okay, because it does go up really high and then we drop down at the very end, okay. So the data is skewed to the right. Remember, when you're describing which way it's skewed, it's kind of, which is that outskirt data, okay, that kind of makes it not look like a mound, okay? Or which side do you have the longer tail on, okay? So then we want to talk about the variability. So the variability ranges from 200 to 400 calories. Okay, which is what some of you guys said. Some of you guys specifically said, hey, it's from here to here. Okay, and the last one is center. Where do you guys think the center of this data would be? Tyler, what do you think? Okay, probably about 200. Is it really clear on this one where the center is? No, it's not like we have a whole bunch lumped together in one spot and you can tell. Okay, but if you were going to pick, 200 would be a reasonable center. So there is not a very clear center, but 200 calories has the most data. All right, C says, suppose you wanted to report data on calories per cup. So when we're talking about per cup, how many cups is that? One. Remember, this per is a rate. Anytime we have a rate, we're talking about getting this to a 1. Okay, so this is 1 cup per cup. For different soups, what would be the calories per cup for chicken noodle soup? So if you go back and look, okay, chicken noodle soup is 360 calories, correct? But for how many cups? For 4 cups, right? So if we look at this, okay, this is 360 calories, okay, but this is for 4 cups, all right? So we want to make sure, okay, that it's coming up like that, okay? Doesn't, all right? Okay, so when we're doing this problem, you guys should have taken, sorry, it's all messed up now on my paper, okay? You should have taken 360, which is the number of calories, over 4 cups, because there's 360 calories in 4 cups. Okay, we want to get this to a 1, because we want 1 cup. So how do we get 4 to 1? Zach?
Divide by 4.
Yeah, we divide by 4. Divide by 4. Okay, 360 divided by 4 is 90. 4 divided by 4 is 1. So in chicken noodle soup, there are 90 calories per cup. Okay, Bella.
Why do you have to do it that way instead of just doing 360 divided by 4?
I wrote it this way so that you guys could see when you are doing your study guide, you can see where did I get these numbers from and what did I do. Okay, so if you just wrote 360 divided by 4, that's fine. Am I going to need your work?
Yeah.
Yes. I need to see what you divided. Okay, you should not just have 90 calories as your answer. Make sense?
Yeah.
Okay, Jenna?
How are you supposed to know if you're using a round number or the actual?
Okay, so Jenna's question is, how do you know if we use the rounded number or the actual number? This has happened twice. How did we know which number to use? It did not ask us to use the rounded number in the directions, correct? So in the directions for this, it just said, what would the calories be for chicken noodle soup? It did not say, what would the calories be for the rounded number of chicken noodle soup. Okay? You're gonna, but B is based on, is your shape of your dot plot. So did you use the rounded numbers in your dot plot? Yes. So then you would use you're answering based off of the dot plot, where this is not based off of the dot plot. Okay? Any other questions on that? Okay. Could you calculate calories per cup for all of the soups listed in the table? Explain why or why not. So could you find the calories per cup for all of those from our table? No. Who thinks yes? Who thinks no? Who thinks I don't know and I'm just going to wait till Miss Bryan tells me the answer? Okay, that doesn't work because that's not thinking. Okay? Could you calculate the calories per cup, okay, for all of the soups listed? So here's all of our soups. Could you find the calories per cup for all of them? Yes. Wouldn't you just do exactly what you did on C for each one? Would all of them be divided by 4? No. Some would be divided by 3. Some are already on there as 1 cup. Okay, but could you find the measurement for each of them? Yes. Are all of these measurements in cups? Yes. What happens if they are in ounces? Some of you are like, oh, we'll just convert it. That's cool. What if you had a weird kind of soup that's not really a soup, okay, and it was like you had some bread thrown in there. Okay, could you figure out the cups for a slice of bread?
Yes.
Okay. The question is though, can you find the calories per cup? If it told you a slice of bread is 200 calories, could you find the calories per cup?
Yeah.
What's it being measured in?
Slices.
It's slices. So can you find cups if it's being measured in slices?
No.
Okay, so yes, for this one we could. So yes, each soup has a measurement of cups to be able to find calories per cup. Because each of those are measured in cups, we can find calories per cup. Okay, E wants you to decide how would you figure out which one's the healthiest to eat. Okay, so which one of those soups is the healthiest? Would you look in terms of calories? Okay, so which one's the healthiest based on the calories?
1 second.
Okay, would you compare the calorie amount or the calories per cup? So are you going to do the calorie amount to figure out which one's the healthiest or the calories per cup? Well, what do you think?
The calories per cup.
Why?
You should, like, say you have like 4 cups in one soup, and that's like 400 calories, and there's like 1 cup in another soup. Like 2 different soups, that's only 100 calories. Like, you really wouldn't know. I mean, it wouldn't be like fair to measure them which one's healthier, because they could be like the same, like, health for you.
Yeah, so what you're looking at is this smoky ham has 210, but chicken noodle has 360. So if you just looked at the calories, it sure looks like that smoky ham is a lot healthier. But if we did, this is 4 cups. So this really is 90 calories per cup. How much is this one per cup? 210 calories per cup. So which one actually is healthier?
Chicken soup.
The chicken noodle soup is actually healthier. Okay, we're using the same measurement. Okay, you can't compare 1 cup to 4 cups. You have to compare them at the same measurement. Okay, does that make sense? All right, so for B, a father wanted some pieces of wood that were 12 inches long for a building project with his son. He asked a hardware store to cut some longer pieces of wood into 12-inch pieces. However, he noticed that not all of the pieces given to him were the same length. So he took the cut pieces of wood home and measured the length of each piece. That table below summarizes the lengths that he found. So A is create a histogram, okay? So when you are creating your histogram, you're gonna start with your design, okay? Your layout. Okay, what's something you should probably do first before you forget, Alicia? Title. This is a histogram, so do you have to tell me it's a histogram?
Yes.
Yes, so your title should have something along the lines of histogram. Of, and then what are we talking about? We're talking about the lengths of the wood, so of wood lengths. Okay, make sure you tell me what's being described. Okay, after you've done your title, you should put in your X and Y descriptions, correct? Okay, so what's going to be down here? What's going to be down here?
Length in inches.
Okay, the length, right? And then Ryan said in inches. Don't forget, you have to tell me what you're measuring it in. Okay? So we have lengths. Okay, what goes on the y-axis? Cadence? Frequency. Okay, on a histogram, it is always going to be frequency. Okay? On our y-axis. What's the next thing that I need? Tyler? I need some numbers. Okay, so for the X, where are you going to get your numbers from? Cadence?
Well, first we're going to put a 0, right?
Okay, first we got to put a 0.
And then cut them.
And we have to cut it. Why do we have to cut the X line? Joanie?
Because we don't go because we're not going counting all the way up, so we gotta go choose.
Okay. We're not counting all the way up. Remember, this X is a number line. Okay? Anytime that we do a scale on a number line, all right, we have to count by the same thing. But on this, we're not counting by the same amount because, as Giovanni said, we're skipping some stuff. So we're going to cut the number line. And then what number are we going to start with? Ring. 10 and 50 hundredths, or 5 tenths, right? Where did you get that from, Ring? Okay, the length in inches. So basically, these right here, okay, that tells us what we're going to, how we're going to number out our scale. Okay, so we're going to have, our first number is 10 and 5 tenths. Okay, and it goes to 11, so then our next number is 11. Then we have 11 to less than 11 and 5 tenths. So 11 and 5 tenths. Then it goes to 11 and 5 tenths to numbers less than 12. Then we have 12 to numbers less than 12 and 5 tenths. We're counting by 5 tenths each time. Okay, we had to cut this because this distance between here and here is 5 tenths. But from here to here would be 10 and 5 tenths. So that's why we cut the number line so we can use the same scale. Okay, make sense? All right, what do we need to use for the frequency? What numbers are we going to use there? Jakari?
1, 2, 3, 4, 5.
Okay, and Jakari, where'd you get those numbers from?
The frequency table.
Okay, from the frequency table, right? Our numbers are between 1 and 5. Okay, so we're gonna number them off 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Make sure that when you're doing that, that these are somewhat close to the same size width. Okay. Some of you guys were like drawing out like the grid lines. That makes it really hard for me when you grade it. Okay. If you kind of want to have like the grid line, do like a slightly dotted, really light, okay, line so that it doesn't really mess up the grid line. Okay. All right. So now we have numbers 10 and 5/10 to numbers less than 11 is 2. So we're going to start at 10 and 5/10, right? And go to 11. How high does this need to go up? Up to 2. And then over on the 11. Then we're going to do 11 to numbers less than 11 and 5/10. That goes up to 3, correct?
Yep.
So what do we have to do with our graph?
We need to
Yeah, another column.
make sure it's
Our bars have to be what?
touching.
Touching. In a histogram, they are touching because it's a continuation in that number line. Okay? All right, so there is our final histogram with everything that we need on it. So B says describe the shape of the histogram you created. So which shape do you guys think this histogram would be considered? What do you think, Reese? Okay, Reese says skewed right. So let's draw in our thing. Remember, we're going to hit the corners. Of our histogram up and over. Okay. So Tyler, what do you think? He says skewed left. So Reese says skewed right and Tyler says skewed left. Reese says, never mind, just kidding. I don't say that anymore. Right? Because what side is our longer tail, like which side of the data is to the left? Excuse me. How do I say this? When we're looking at the very top of our shape, do we have more data to the left or do we have more data to the right? More of this data to the left. We've got this longer tail on the left. It's not right in the middle. Okay, so this shape, the shape is slightly skewed left. Okay, and just some quick reminders. Okay, when we're looking at approximately symmetric, it's going to look pretty much like a mound shape. Okay, or really close to it. So this would be approximately symmetric. Okay. All right, this would be skewed left. Okay, because there's data to the left of that top center that kind of makes it have this longer tail on the left. And then skewed right would look more like that. We've got some data points out here to the right of the center that skews it. Okay? Okay, so that's what the three of those look like. We're explaining based off of the histogram, okay? we need to be making sure that our answer talks about the histogram. So this says without calculations, remember? Okay, we're trying to figure out how many data points, okay, or excuse me, what we're looking for is the mean, what's the mean going to be? So right now, if we think the mean is 12, okay, 12 to less than 12 and 5/10 and higher would be these ones, correct? So that would be this section of our histogram. Okay, then, okay, if we want to look at these ones are less than 12, correct? That would be this part of the histogram. Everyone good? Okay, so now if you look at those, you're like, well, Miss Bryan, there's 3 bars and 3 bars, so has to be 12, doesn't it?
Yeah.
Okay, but what do we know about mean? If we have lots of big numbers and some small numbers, our mean is going to be what? It's going to be higher, isn't it?
Yes.
Because the more higher scores there are, the higher the mean happens to be. So if we looked at these, okay, this is 5, correct? This is 4, okay, and this is 1. So how many pieces of wood are bigger than 12 inches? 10. Okay, so there's 10 boards that are 12 inches or more, correct? Over here, this is 2, right? This is 3, and this is 2. So how many boards are less than 12? 7. So they're not even, correct? If there was 10 on one side and 10 on the other side, 12 would be your mean. Got it? Okay, but we have more higher boards over here, which means we're going to have a higher mean. Does that make sense?
Yeah.
We have more boards at a higher length, so the mean is going to be higher. Okay, what happened if this side was higher? The mean would be what? Less than 12. Okay, so if the number of boards is the same, the mean would be equal to what we said, right? It would be 12. Okay, if there's more boards higher than 12, it's going to be a higher mean because there's more over here. That's going to increase the mean. If there was more over less than 12, it would be a what? Lower mean. Okay, Zach?
How did you figure out how to split that? Did you just split because 6 changed that?
Why did I like these 2 areas up here?
Yeah.
Because it asked me if the mean is 12. So this is 12, okay? And then numbers less than 12 and 5/10. This is numbers, this is 11 and 5/10 and numbers less than 12.
So all you did was add the numbers in each column,
Uh-huh.
red and green, and then you figured out which one.
Yeah, but our answer has to be based off the histogram. So you guys can't just write your answer based off of this table. You can use the table to help you, but your answer has to be based off of the histogram. Okay? So I'm going to show you how the sentence would look. But do you have another question?
Yeah. How would you know if it's greater or less?
It depends on how many things. So this, we have 10 boards that are greater than 12, and we have 7 boards that are less than 12. So since there's more that are greater than 12, it's going to be higher than the mean.
Okay.
Okay? Or the mean will be higher than 12, I should say.
Okay.
Okay? All right, so flip right on over to where you to write your answer. Okay? So remember, oops. Oop, sorry, got my finger right in the way on that one today. Okay? All right, so remember we are doing this without calculations, right? So don't go through and calculate it. Don't waste your time. Because if you're like, if your answer is, no, the mean is 12 and 3/10, I'm going to say, that's awesome. You didn't actually use the histogram, which is which is part of the direction? Okay. Okay, so the mean will be more than 12 because there are more data points or pieces of wood or whatever we're working with, okay, above 12. Remember, there were 10 of them, okay? Then below 12, remember there were only 7 that were below 12. So since there's more above 12, the mean is going to be higher than 12. Based on the histogram, should the mean absolute deviation be larger than 5/10 inches or smaller than 5/10 inches? Okay, so now we're looking at the mean absolute deviation. Okay, so we want to know at that deviation, okay, or is it going to be bigger than 5/10 away from the mean or smaller than 5/10 away from the mean? Okay. Okay, on this one, I am not going to give you the answer. I am going to give you the, hey, this is what you need to look at portion. Does that make sense? Okay, so I'm going to tell you what you need to decide, like what are the factors that you would need to decide how to answer the question. So I'm not actually going to give you the answer to this question. Okay, remember that your mean absolute deviation, okay, is your distance away from the mean. Okay, so when you're looking at that, are most of your data points, okay, within that range or are they outside of that range? Okay, so let's flip over. Okay, so you need to look at the deviations. Okay, are most of them bigger than 5/10 inches or smaller than 5/10 inches? Okay, so Caden's question is, hey, we don't know what the mean is for this problem because you weren't allowed to do calculations in this one, do you? Okay, we do know that the mean is going to be above 12, but it's not going to be a lot above 12 because these aren't like super far away. Okay, they're almost balancing each other out. So what you're looking for, okay, is if you had your graph, all right, here, okay, and you have your histogram, okay, and you said this was the mean right here, okay, let's say these are 1, 2, and 3, okay, if this is your MAD between here and here, right, because your MAD is 5/10, so 5/10 this way, 5/10 this way, okay, so I should have put this up top actually. Okay, so on average, they would be 5/10 away from the mean, correct? 5/10 to one side, 5/10 to the other side, okay? look at what you have on the outskirts of it. Do you have a lot of numbers on the outskirt of it? No, this is 1 and this is 1, correct? Where's most of your data?
2 and 3.
Isn't most of your data within the set of deviations?
Yeah.
Is it most of your data right here?
Yeah.
You have 2, you got 3, and you have 2, right?
Yeah.
So that's 7, right? 7 out of your 9 data points are within the MAD deviation, correct? Okay, so wouldn't the MAD be close to this?
Yeah.
Isn't the MAD going to be close to 1/2 inch?
Yeah.
Because most of your deviations are within 1/2 inch of that shape. Okay? So, you might want to draw that out so that you know. Okay? So, that's your MAD. You've got, your mean is here. This is 5/10 to the left. This is 5/10 to the right. Okay? So these data, these sets are within the MAD. Okay? Save some time. Suppose this project was repeated at 2 different stores and the following 2 dot plots of board lengths were found. Would you have a preference for one store over the other store? If so, which store would you prefer? Why? Why? And then justify based on the data distribution. So basically what they did is the first guy went to Home Depot. So this guy's like, all right, I'm going to go to this Home Depot over in Surprise. You go to this Home Depot in Paradise Valley. You get some 10 boards or whatever. Let's figure out what, if we're going to get the same size. Okay, and then we'll figure out which store is better to go to. Okay, so they already calculated for you for store 1, the mean and the MAD, and they rounded it to the nearest 10th. Okay, then for store 2, the mean is 11 4/10 and the MAD is 4/10, again rounded to the 10th. So the means are almost the same, correct? Okay, so this was yesterday's lesson. So based off of looking, okay, the means are almost the same. Which store would you prefer to go to if you need 12-inch boards? Which store would you go to if you need 12-inch boards? Okay, remember these are our boards that are 12 inches. So we want 12-inch boards. Which store would you go to? Oh, Miss Brain, they both have 4 at the 12. So now what am I going to use to decide? Haley, what do you think? Okay, Haley says let's use the MAD, right? So which store would you pick based off of the MAD? Emily? Okay, Emily says store 1 based off of the MAD. Who agrees? Who disagrees? Emily, why do you disagree with yourself?
Because we need to find the one with the smaller MAD.
Yeah, remember, we want the one with the smaller MAD, okay? Because that means it's closer to the mean. The smaller the MAD, the closer to the mean we actually are. So we would pick store 2. Why else would you pick store 2? So not just based off of the MAD, because look right here. Justify your answer based on displayed distributions. Did it say justify it off of the MAD? No. You can use the MAD to help you figure out which one's the best one, but your explanation needs to be about the displayed distributions. Okay, so what would you pick, Darius, and why?
Store 2 because it's more consistent. There's less variability, so
Okay.
you have a higher chance of getting what you need.
How do you know based off of this distribution that there's less variability though?
Because they're all closer together. All the data is closer compared
Okay.
to store 1 where it's all spread out across the graph.
Remember, we use numbers. Use numbers. In our justifications, we use numbers. Kaylee?
If you look at the mean, 11 5/10, in store 2, it has a higher
But we want to do it based off of these distributions. So we're going to look at the data points. So, Kaylin?
Okay. So on store 1 it has the 10 right there.
Uh-huh. So we got 1 on the 10.
Yeah. And then on store 2 it doesn't have that.
Okay, so store 2 doesn't have anything on the 10, so its smallest board is 10 and 5/10. Okay, you could say that.
And then
Okay.
there's 4 on 11 and 5/10.
Okay, and there's 4 on 11 and 5/10 where there's only 3 on here. So what you're doing is you're looking at how is that data distributed throughout it all. Okay, so let's write down our response. Okay, so I would prefer store 2. Remember, if so, which store? You gotta tell me which store you prefer. Whoopsie daisies. Okay. You've got to tell me which store, and then you need to justify your answer based on the data distribution. So are you going to tell me the MAD?
Yeah. No.
No. Do not tell me the MAD. You can use the MAD to help you make your decision. Don't use the MAD in your justification. So I would prefer store number 2. Store number 2 has 4 boards, more than 1 inch, bless you, away from 12 inches. Okay, because remember, we want boards that are 12 inches long. Okay, so we've got 4 boards that are 1 inch away. Okay, so here's 12. So here's like, how do I want to say this? Like this is 1 inch right here, correct? This is 1 inch total, right? Half an inch to the left, half an inch to the right. Okay, so we've got 1, 2, 3, 4 that are more than an inch away from what we want. Okay, where store 1 has 4 boards more spread out than 1 inch away from 12 inches. Okay, so these two are close to our 1 inch mark, but if we looked here, here's our range of 1 inch, half an inch smaller, half an inch bigger. Okay, there's still 4 boards here, aren't there? But aren't they more spread out? Where here's 4 boards right here. Aren't these ones more compacted? Okay, these ones are closer to each other. And you've got more on the 11 inch. These aren't these spread out more? So their 4 boards are more spread out. Okay. Okay, suppose you are timing how long it takes a car to race down a wood track placed at a 50-degree angle. The times for these 7 races are recorded. The mean time for the 7 races is 4 and 5/10. So we want to make sure that we realize there's 7 races that are occurring. Okay, and the mean time for those 7 races is 4 5/10 seconds. Okay, so they already found the mean for us. Okay, so A, what is the total time for the 7 races? Okay, so we want the total time. How are we going to figure out what the total time is? What do you think we would do? Ian?
Multiply 7 times 4.5 to see what that gets and subtract numbers to see when you get to 0, then add the sum of those.
Okay, can we find out what the actual race times are? No, but it wants the total of the race times, right? So the total, okay, would be the 7 races summed together, isn't it? Okay, so team 2, there's 6 of you. You all race your cars and Kaylee races with you. Your total time is what all 7 of you got together, correct? I don't need to know what Kaylee got. I don't need to know what Cadence got. I don't need to know what Lindsay got. I need to know what the total time is for the 7 races. Okay, well, they've only given me the mean. So we know that mean equals our total, correct? Divided by the number of data points. Okay? So to find mean, we have to take our total, and then we have to divide it by the number of data points. Okay, so what information did they give us that we could fill in? If we wanted to make this an equation, what did they give us, Tyler? They gave us the mean. What's the mean, Tyler? 4 5/10 seconds, correct? Is our mean. Do we know what the total is?
No.
Nope, so we put in a variable, correct?
Yep.
Divide is just a division symbol. Do we know the total number of data points?
Yes.
Yeah.
Oh, yeah.
How many people raced?
7.
7. There are 7 races. So our total number of data points is 7. So now that I have an equation, can I solve for x?
Yes.
Okay. So let's remember. Who remembers how we solve for x? Tyler? Okay, but why? Because we have to solve for x. So what do we have to do with x? To solve for x, you have to do what to it? Cadence?
Cancel out the 7.
You have to cancel out the 7. You have to get it by itself, correct? So how do we cancel out divide by 7?
Oh, shit.
Christian?
Do you do 7 divided by 7?
No. How do you cancel out divide by 7?
Keep changing.
Olivia?
Well, you multiply 4 times,
Just this part first. How do we cancel out divide by 7?
you multiply it by 4.
We multiply by 7, don't we? What's the opposite of division? Multiplication. So if I'm dividing by 7, if I multiply by 7, this will cancel. But if I multiply by 7 here, what do I have to do over here? Multiply by 7. We got to do the same thing on each side of the equal. Okay, so 7 times 5 is 35. 7 times 4 is 28. 29, 30, 31. We've got one number behind the decimal. So we want to move it 1 to the left. So this is really 31 5/10. So x equals 31 5/10. So what's the answer to our question? Darius? Oh, it wasn't you that said that? Cadence?
The total time for the 7 races is 31 seconds.
There you go. So the total time is 31 and 5/10 seconds. Make sure you answer the question correct
Yes.
in a sentence. Are there any questions on what we did? All we did was plug in all the information that we had, which we did that a lot with equations. We did a lot of plugging in what you had, okay? And then figuring out how to get the variable by itself, okay? Suppose you learned that the time malfunctioned for one of the 5 races. Okay, so we've changed this, right? This is 5 races now. The result of the race had been reported as 2 and 4/10 seconds. If you remove that time from the list and recompute the mean for the remaining 6 times, oh, actually this is really supposed to be 7.
Oh, sure.
Okay, sorry about that. It was a typo. So if you remove the time from the list and recompute the mean for the remaining 6 times, what do you think's gonna happen to the mean? Okay, so what they decided is, hey, this time got messed up, this 2 and 4/10 got messed up. What do you think's gonna happen to the mean now? So Kaylee's time got messed up, so she's no longer part of the race. Okay, we're only going to calculate for the 6 people at group 2. What's gonna happen to the mean? Is the mean gonna go up? Is it gonna go down? Or is it gonna stay the same if we remove Kaylee's data? Okay, so because of the malfunction, we are taking out the reported 2 and 4/10 seconds. Okay, so we're removing that from our data set. 2 and 4/10 is less than the mean. Okay, remember our mean was 4 and 5/10. Correct? So when I take out a number that is less than the mean has to go up. I'm canceling out, I'm getting rid of this small number. So when I get rid of a small number, okay, the mean gets to get bigger. What happens if I got rid of a big number?
Then it gets smaller.
The mean would get smaller. Okay? Remember, this is only a little bit of time. Okay, so she's sharing just this little bit of time. All right, so the mean will go up. Because we removed a number less than the mean. Okay, so we removed a number that was less than the mean, so the mean has to go up. Does that make sense? Okay, so when we looked at those 3 charts that we did on the board, we had 17, 18, and 19. Okay, we have a mean of 18 when all of our dots are on 18. Okay, and then if we decided to take one of those dots and put it on 17, we know that the mean goes down. Okay, we don't know what it's going to be. We just know that the mean goes down, correct?
Yeah.
Okay, but what we're doing for this problem is we are getting rid of one of those. So now our table looks like this. So what happens to the mean? Okay, from here to here, the mean what? It's going to go what? Up. Because this is less than 18, lower than 18. The mean is back at 18, so didn't it go up? It increased because we got rid of this lower amount.